now that everyone's excited about applications of AI in the real life, I was checking this AI for Finance Foundation and what they've done. One of their works is the FinGPT, which is kind of a chat GPT or LLM model, which is fine-tuned for applications in finance. And here you see their models are based on Llama 2, Llama 2 7 billions, and also ChatGLM 2 6 billion parameters. And if you compare it here, the cost for the fine-tuning here is only $17 and 17 hours, and they run it only on one RTX 3090. So compared to other models that are listed here like GPT-4 or the original Llama, or even the Bloomberg GPT, which costed around $2.67 million and 50 days to train for Bloomberg, and 512 800 graphic cards, you see the performance is much better in FinGPT. So the idea today is to see how we can reach this level of performance with this amount of investment. All right, well, maybe this comparison is not totally fair, because what you see here is the total cost of training the model. But what you see here is the cost only for fine-tuning a model that is freely available and publicly available. So the cost was already paid by someone else when they were training the models. For our experimental project here, I chose the FLAN T5 model. It's a Google model with a specific text-to-text translation transformer architecture. It's the upgrade of T5. It has been around for some time now, as you can see. This benchmark and this article is around 2 years ago, even more. And this model, it's even more efficient in terms of resources compared to FinGPT, which is based on 6 or 7 billion or 13 billion parameters. So it comes in different sizes, T5 small and FLAN T5 small, with around 80 million parameters. And you see we have base large, X large, and double X large models with higher number of parameters. And when you compare here their performance in different benchmarks for AI models, you see that at X large we already reach a good level of performance, and here you can see it's comparable to GPT-3 or the GAL model with 120 billion parameters. But this model, it has only 3 billions. So this is why I chose this one. And the other thing that's important is that the structure of this model is that everything ends up to a text-to-text generation. So this is one of the reasons why this FLAN T5 model is very efficient in terms of fine-tuning for instructions. The FLAN T5 model is publicly available on Google's page on Hugging Face. So if you come to this page and you scroll down to collections here, you search for FLAN. Here you have all the releases, and you can easily download and access this model and use it for inference. So in this video, we are going to compare these models from the smallest one to the largest one and see what is the model that suits our application. And one thing that's important here to remark is that I'm using only CPU. So my system here, it has a 10th generation CPU with 10 physical cores and 20 threads, 32 gigabytes of memory, and no graphic cards. It's only the onboard one in the CPU. Well, you can read all the details on this model, how you can use it, the languages that are included, how to run it on CPU, GPU, or other devices, and other terms of use. So let's go to our code. I'm using the task which is text-to-text generation or sequence-to-sequence generation, which is the only task that FLAN T5 supports, but it can be trained for different instructions. As I said before, it's only down to text when it comes to the FLAN T5 architecture. So I download these with the pipeline method, and now I'm storing them on my local drive. As you can see, they've been saved already. I won't run this code because it takes some time. Let's come here, assuming that I have my models saved already here. I can call again the pipeline, but this time, instead of giving the Google repository address on Hugging Face, I'm giving it the local address that I have. So now I have a model list which has the models and their names inside. We can see it here. Alright, so here I'm testing a simple task. I have a paragraph about the Federal Reserve and how it reacts to recessions and inflation, and the task is to summarize the above text. I've already run the small model 0, and you see that it's not doing that well because it's giving me only the first sentence, no summarization here. We can run the other ones and see how they respond to this. Same story. I think even the third one, number 3, which is the X large model, is not going to work well. Well, this is the challenge with the FLAN T5, which is you need to do some instruction fine-tuning before being able to really benefit from its good performance. Well, you see the X large model on my CPU, it takes some time to run. Okay, we got another sentence again. So at summarization is not good. At questions I've tested already, it seems not to be that bad. I have a question here. I'm asking the largest model that I have, the X large, and let's run it again and also see the performance of the system at the same time. You see, it seems to be using all the threads available at the same time. Of course, a lot of memory is being used, but yeah, my CPU temperature is also increasing, but you see we still have a lot of margin until the full application of the system resources. So the question that I had was, I bought 2 apples and 3 oranges. I put 2 in numbers and then 3 in letters on purpose to see if it understands well and can calculate them efficiently for $10. So in the end, this is the price of the orange. What is the price of each apple? It does the calculation. It seems to be good. Each apple is $2. Oh, perfect. And here I did a list of sample questions, and I'm asking this model again. As we can see here again, it takes a lot of time, around 1 minute for only 4 questions, and you see the resources are not fully used. I would prefer to have my CPU at 100%, but faster response. Okay, I will stop this one because it takes some time. So what I've done is something that you might want to do when you are doing the inferring locally for testing purposes or for even real use cases. So I'm using the threads library of Python, and for each module and each prompt I'm launching a thread, and then here I'm defining the arrays. Here I'm launching the threads and storing all of them in a list called threads. And then for each thread, when you launch, you cannot monitor it anymore unless you join it. So here you run this, you define the function. At this step I'm launching the threads, and then here I'm joining them one by one, and at this stage you can see the resources of the system. Well, all the models were loaded quickly. Here you see a jump in the disk usage. Also, the memory is not that far from being full, and the CPU load now is very, very high. All right, so here you see it's taking some time, and this is the behavior of the system when you're using threads in Python. You're waiting here in this loop, but the outputs are being added at this stage. All right, so it took around 1 minute to respond to all of them, and if I let this one run, it takes 1 minute only for the third model to respond to these 4 questions. And you see that if we use threads, all models respond to all questions in the same delay of 1 minute. So the performance is increased here. And here, let's compare the results. I will run this again. All right. So the question is how old is the planet Earth? And you see a small model is wrong. The large model says just billions of years, but the base model and the X large model are good. This seems not that bad. Next one is just a Python method or code to return the sum of the elements in a list. Well, the small one is not doing anything. The base and the large and the X large, all of them seem to be correctly calculating the sum of the elements in a list, except that all of them are expecting a list at the input. Well, this is not a problem. Anyways, they don't seem to be up to date. So the president is still Barack Obama or Gerald Ford or George W. Bush. So it's a bit old, the database that they've been trained on, or they are not trained to give the most recent response. All right, anyway, this is a bit more specific questions regarding the hedging against the volatility of the Forex market, and you see a small model and the base model are not good, but the large and X large, they give good responses. Most of the X large, the large one is saying hedging with a foreign currency, but okay, we can accept that anyway. So the next subject is loading and using and fine-tuning quantized models. So the benefit of using quantized models is that they are going to need less memory. This is for sure. So you know that if you load a model in 8-bit or in 4-bit mode, it's going to take less memory, it's going to take less space on your disk. Here I have an 8-bit version of the X large model that I've downloaded directly from a repository on Hugging Face, and let's see the difference between these models. So the X large model originally is 10.6 gigabytes and this 8-bit version is 2.66, so around 4 times smaller, and I think it's around the same size as the large model. So the size that you see here on disk is more or less the same size that it's going to take on your memory. So it's very efficient in terms of memory usage, except that you are going to lose some accuracy. And what's more important, and what's the reason why I'm not going to use quantized model in this video and in the next, is that your hardware, your CPU, GPU or GPU, whatever device that you use for inference and also for training and fine-tuning, has to support directly the 8-bit or 4-bit calculations. So in my case, my CPU does not support the 8-bit calculation. So whatever I do in terms of 8-bit data storage and the mathematical operations, it needs to first convert the 8-bit to 32 bits or 64 bits and then do the calculations. So not only it's not going to be faster, but it's going to be slower because I'm adding in a step here. Let's see for ourselves. So I'm going to load this 8-bit model, which is compiled by someone else. Same questions as before, and let's run it. Okay, it responded in around 44 seconds. So you see this model was able to respond to all questions in around 45 seconds, and also the results are not that different from the original XLarge except for the Python code, which is, well, like an infinite loop. Okay, here is talking about transactions. Here we have contracts, and okay. So what I'm going to do next is that I'm going to load directly the 8-bit and also the 4-bit versions of the XLarge model. All right. To do that, you will need the bits and bytes library, and we'll need a bits and bytes config here. So what you need to set in this configuration, the quantization configuration, is that you want to load it in 4 bits or 8 bits. So what I'm doing here is that I'm loading a model, the original one, then I'm loading also a quantized one for 8-bit and another quantized one for 4-bit configuration, as you can see here. So I've done this already. It takes some time. So what I did is that I've also saved them in different folders, and here I'm going to directly load them again. So here I have 3 models. I want to just compare them in terms of performance in responding to a single question here. So when you're loading a model, an LLM model with the transformers library, you can also use the tokenizer and the model directly. So the T5, it has its own tokenizer. You can also use the auto tokenizer. The auto tokenizer in the transformer library is also able to find out the good parameters, but I'm using the T5 tokenizer here. And also for this T5 FLAN, we already saw that we have only the sequence generation, which is called here for conditional generation. So I'm loading the model. Device mapping is auto, so it will be running on CPU in my case here. I have the input, which is the same question that we had before about the price of apples. And firstly, what we do is that we tokenize this input. Then we pass these input IDs to the model, and here we are using model.generate method. So let's run it for first one, second one, and the third one. So I've done this already, but I'm going to just run it again so we can check together how it goes. As you can see, it took only 9.9 or around 10 seconds for the first model, which is the original XLarge model, to respond to this question. But let's compare it with the 8-bit and the 4-bit models. As I explained before, I'm running a CPU, and all the models in my CPU which does not have the native 4-bit or 8-bit calculators have to go through the conversion phase where it takes the 4-bit or 8-bit parameters, turns them into 32 or 64 bits, and then does the calculations. So this is why we'll have additional steps, and these models are going to be slower compared to the original one. As you can see, 10 seconds compared to around 28, and this one's still running. So in the meantime, I want to also rerun this part that I did for this model. for the original X large model, but using this T5 conditional generation method, not the pipeline, because the pipeline in terms of speed and efficiency, it's not efficient compared to this approach. So the input text equals prompt, it's tokenizer, and the method is different here, and then also the result is different. Let me copy paste that part. Alright, so the outputs are model.generate, and then, well, we don't have the hypothesis here. And we use tokenizer that decode outputs, nothing more. Okay, I have a rare element. Alright, that's it. You see the 4-bit model is still running. Yeah, now it's finished. Okay, so 2 minutes 43 seconds, and you see in terms of accuracy, at least in this question, they all responded identically. So sometimes they give the same response, sometimes not. It depends on the question and what is the path of the whole data and the calculations. But normally we expect the original model with the higher to be with the one with the highest accuracy. All right, let's run this one. Well, it seems that I made a mistake here. Yeah. So here it's input text equals prompt, and then we have the input text as the input. The input ID is going here. Yeah, this is a problem. Input tokens are going as the input of the generate function, and the outputs is coming here for decoding. Now let's run it again. Same response as before. Well, this one doesn't seem good, especially because we don't have the special character in the end. The ending token doesn't exist in this one. Well, anyways, it took only 20 seconds. Anyways, what we see is that the X large model, when run using this approach, is much faster than the pipeline approach, and also much faster than even this efficient 8-bit version that I downloaded from somewhere else. And even compared to this one, it's this 8-bit or 4-bit that I downloaded from the Google repository, it's faster. So the conclusion in the end is that FLAN T5, it runs well even on the CPU. You see, it takes some time for the X large or the large model, but the base one at least was very fast. It is because it's a small model. The base model, it has only 250 million parameters, which is pretty small. And what I'm going to do next is that I'm going to take this one, and using the parameter efficient fine-tuning approach without any quantization, to fine-tune it for sentiment analysis on financial headlines and news. See you soon.